A microwave oven does not heat food by heating the air. It heats food by moving energy directly into certain molecules and letting that motion become heat. Think of it as a simple chain. Energy, molecules, heat. Inside the microwave is a device called a magnetron. It produces microwaves at about 2.45 gigahertz, billions of oscillations per second. That frequency is especially effective at interacting with water molecules. Water molecules are not electrically neutral blobs. They have a positive side and a negative side. This makes them tiny electric dipoles, like microscopic bar magnets. When the microwave's electric field flips back and forth billions of times per second, those dipoles try to follow it. They rotate, they twist, they collide with neighboring molecules. That motion turns electromagnetic energy into thermal energy. Energy, molecules, heat. This process is called dielectric heating. The field pushes. The dipoles respond. Random molecular motion increases. Temperature rises. Heating begins where the microwave energy is strongest, then spreads through the food as heat conducts outward. Why water? Because most foods contain water, and water responds strongly at microwave frequencies. Sugars, salts, and fats can absorb some energy too, but water does most of the work. That's why moist leftovers heat quickly, while dry crackers barely warm at all. So why does the container sometimes stay cool? Materials like glass and many ceramics contain very few mobile dipoles at this frequency. They don't absorb much microwave energy. Instead, they heat indirectly, by contact with the hot food. Energy, molecules in food. Heat, conduction into the container. Microwave-safe plastics behave similarly. They absorb very little energy and warm mainly through contact. Metal behaves differently. Metal reflects microwaves. Sharp edges can concentrate electric fields and cause sparks. That's why metal stays out of the microwave. If microwaves fill the oven, why does heating feel uneven? 2 reasons. First, field patterns. Inside the metal box, microwaves reflect off the walls. The waves interfere with each other, creating regions of stronger and weaker fields. Hot spots form, cold spots form. Where the field is stronger, molecules move more. Heating is faster. Turntables and internal fans help shift food through these regions to even things out. Second, food physics. Microwaves don't heat infinitely deep. They penetrate only a few centimeters into dense, watery foods. The outer layers absorb most of the energy first. The center warms later, mainly through heat conduction. Thickness matters. Water content matters. Salt concentration matters. Air pockets insulate. Frozen food complicates everything. Ice absorbs microwave energy less effectively than liquid water. So edges melt and heat while frozen centers lag behind. This is why stirring matters. Stirring redistributes energy. Resting time allows conduction to smooth out hot and cold regions. What about friction? At the molecular level, dipoles lose energy through collisions, called dielectric loss. Friction is a helpful mental picture. Microwaves make molecules wriggle. Wriggling and bumping turns motion into heat. You might notice the plate is cool at first. That's because it absorbs very little microwave energy. But once hot food sits on it, the plate heats by contact. Field, water molecules, heat in food, heat into plate. To reduce uneven heating, spread food into a thin, even layer. Cover loosely to trap steam. Steam helps move heat. Use the turntable and don't block it. Pause and stir. Let food rest before eating. Use microwave-safe containers and avoid sealed lids. Microwaves deliver energy to dipoles. Dipoles move. Collisions turn motion into heat, and conduction evens it out. Energy, molecules, heat. So the next time you reheat leftovers, Imagine an invisible field nudging billions of tiny water dipoles, all rotating, colliding, and warming your food from the inside out, then slowly leveling as heat spreads. Simple cause and effect, happening billions of times per second.